Hey guys, today we're going to be going over the function of the nephron, reabsorption of certain solutes, as well as some things that stay in the tubules of the nephron. We're going to go over filtration, how that works with the solutes, and then we're also going to describe blood flow to the glomerulus and glomerulus filtration rate. So today we're going to be looking at my notes. I've drawn it out here. First off, here's our basic makeup of renal corpuscle. You have the Bowman's capsule, you have the glomerulus. Everything that goes through here gets filtered through the glomerulus, and that is done so by a filtration slit. So what happens in a filtration slit is you have four different layers. So you'll have a fenestrated membrane or endothelium, a basement membrane, and then a podocyte foot and a filtration slit. So going through all these different filters will filter out your solutes over here. So some filtered substances would be water, glucose, sodium chloride, amino acids, other small proteins, metabolites, urea. Things that stay in the blood would be medium or large proteins, red blood cells, white blood cells, and platelets. But on top of that, we have a whole bunch of other solutes. So we're going to jump over to tubular reabsorption here. So as you can see, we've drawn it out, and in each different section you'll have your corpuscle, your proximal convoluted tubule, the loop of Henle, the distal convoluted tubule, and your collecting duct. And each of those sections will do something different. So if we're looking at sodium, it's going to be a main transporter for most of these solutes like glucose, amino acids, and lactate, and they're going to transport into the cell. And if we see these dotted lines, that's our cell. They're going to transport all those things into the cell. And then on the other side, there will be other ion channels or antiporters, which will transfer things out. So sodium, because it's moving in, can then also move out certain other things like bicarbonate, which is important in maintaining alkalosis of the blood or acidosis, regulating that. Sodium, because it's also in or outside of the cell, it can antiport amino acids or lactate out into the blood and pull sodium in. And so that's an antiporter, which moves things too. Water, if we can see here, will go through aquaporins that go all the way through the cell, and this will happen in certain parts, but mainly you can go through the cell through aquaporins, or if you see here on the parts of the cell, or like the intersections between cells. So if we were to draw a line here and a line here, those are two cells. Water would just transfer straight through that gap and pull sodium and chloride through. So that's important too. Let's see, where did calcium go? We need calcium. Calcium also in the proximal convoluted tubule will be dragged over with the water. So if water's moving over here and it contains calcium, it can be dragged over. So that's an important mover. Finally, so we've covered sodium, we've covered glucose, we've covered amino acids, we've covered water, chloride, and I think that's everything. So it's gonna carry things over. This side of the cell is for the blood, and this side of the cell is for the tubular fluid. So it's through different sections, and if you can see here, there's lots of different sections of the nephron that will transport different solutes through. So if you see interspersed here, you have a lot of sodium moving in and acting as a transporter, symporter for lots of substances. And then you'll also have leak channels, but you'll also move chloride in that can act as an antiporter for bicarbonate. So there's a couple things that we need to consider when we're moving different solutes. Okay, so we're gonna talk about renal threshold and saturation, if I can find it here. So renal threshold is when, and we just talked about it, there's a bunch of ion transporters. First, I think, let's talk about, well, yeah, renal threshold and saturation, right? So we're moving certain substances across. For example, glucose or PAH can be moved across. You can also move across things I've already mentioned, like amino acids, glucose, sodium, etc. But there's a point where all of the channels or all the transporters are saturated, so you can't move any faster. And so this is evident in here, in this graph here. So we have urine concentration on the left and plasma concentration on the right. This is with clearance, you're measuring the rate a substance is filtered back into the blood versus whether it's excreted. And that has to do with filtration. So if you're taking GFR, which is your glomerular filtration rate, inulin and creatine, they are filtered completely. So in the blood, if you were to take a sample, you would have 100% inulin concentration there. And then if you were to take a sample of urine, then you'd have 100% of concentration of inulin there as well, meaning that the nephron did its job. It completely filtered out inulin/creatine, and you had an equal ratio of urine and plasma concentrations of inulin. Other things like glucose will reach a certain saturation point wherein there is more in the plasma than there is in the urine. Glucose, for example, should be filtered out completely and reabsorbed entirely. But if it is not, then you see this point, there's a saturation point above 180 milligrams per deciliter. That's your renal threshold. PAH will do the same thing. It can become saturated a lot quicker than glucose because it is a competitor for certain receptors and transporters, but it will get filtered out way quicker. As you can see, urine concentration is way higher very quickly with our plasma concentration. And so if you reach renal threshold, then you're going to start excreting a lot of things, or you're going to have a lot more things in the plasma increasing because the tubules can't excrete everything, or secrete everything and then excrete it. So that's clearance. Let's see. I went over filtration with your different layers. Okay, blood regulation. Let's talk about blood regulation for the glomerulus. So in your glomerulus, you have here's your glomerulus, right? And here you'll have an afferent arteriole, and here you'll have an efferent arteriole. And within these arterioles, they're carrying blood, and they have hydrostatic pressures. You also have BCOP, which will be an osmotic pressure flowing in there. And so within the arterioles, you'll have hydrostatic pressure of, let's go to the glomerulus. Hydrostatic pressure of the glomerulus will push it out. That will be 50 to 55 millimeters of mercury pushing out. And then, sorry, that kind of looks nasty. And then you'll have 30 millimeters of mercury from the Bowman's capsule, the surrounding structure, and that will push back into the glomerulus. And then finally you have BCOP flowing in the arteriole itself, and that's going to account for, oh, sorry, I misspoke. BCOP's pulling in 30 millimeters of mercury of pressure, and then hydrostatic pressure of the capsule is going to be pulling in, or pushing in, 15. And overall, that's going to come out to 10 millimeters of mercury out of the glomerulus. So it's pushing out 10 millimeters of mercury of filtrate at a time, and that's because of these pressures that happen. Blood flow. So we want to maintain a pressure within the glomerulus of about 55 millimeters of mercury. And in order to do that, what happens if your systemic blood pressure drops? Then you can't filter anything. So in order to regulate that, you have to constrict or dilate afferent or efferent arterioles. So let's say blood pressure drops systemically. You need to increase the blood pressure in the glomerulus so you can actually filter. You're going to constrict your afferent arterioles, which will continue to filter out stuff even though you have a lower blood pressure. Conversely, if you have a low blood pressure, or if you have a low blood pressure, then you'll dilate those arterioles, the afferent arterioles, so you can maintain a higher pressure before you hit the glomerulus. And you'll also constrict the efferent arterioles, this one right here, to maintain a pressure on the opposite end of the capillary. I think that wraps up everything I wanted to talk about. So just as a review, we covered which substances were filtered and reabsorbed, and we talked about some of the channels that go hand in hand with that. We also talked about filtration, what parts are important in that. The mesangial cells, podocytes, your basement membrane, and your fenestrated endothelium. These are all just filters that can vary by size and charge of what you're filtering, that are specific to each of those things. And glomerular filtration rate was over, we'll just over here. Glomerular filtration rate had to do with your concentration in the urine versus the plasma. And if you're filtering something 100%, then you'll find equal concentrations in your plasma versus the urine. And I think that wraps up our answer to question 1 for this essay. Hope that was clear enough. And I'll see you guys in the next video. Ciao.